something changed. On October 29, 2025, as the interstellar visitor, now catalogued as 3I Atlas, skimmed through perihelion, it refused to behave like any comet in the textbooks. Instead of a neat, predictable brightening curve, its output jumped fast, hard, and by a factor that caught even seasoned observers flat-footed. Instruments on SOHO, Stereo A, and GOES 19 caught a stretched, faint smudge hugging the sun's glare, elongated, yes, but lacking the dusty, sweeping tail our instincts expect. Spectra turned bluer than the solar continuum, with signatures of C2 and amidogen that scream active sublimation. Radio measurements suggested that in the 2 weeks before perihelion, 3I Atlas was dumping water at a rate nearly 40 times higher than a month prior, as if a cosmic fire hose had been cranked open. Those are the facts as they first landed, stubborn, inconvenient, and uncomfortably at odds with standard comet physics. One popular first-order model tried to tame the chaos. It imagined that CO2 outgassing at several AU formed a parasol, cooling the nucleus and keeping H2O trapped until the gas blanket thinned. Drop the shield, expose buried ice to solar flux, and bam! Explosive activity. It's tidy, it's plausible. But it doesn't fully square with everything we saw, from the tail that wasn't there to the timing that was almost too abrupt. Another line of thinking points inward, to the nucleus itself. 3I Atlas didn't grow up here. It formed around a different star, in a different disk, with a different recipe. If the internal structure was assembled under alien thermodynamics and chemistry, why would its near-Sun behavior map cleanly onto solar system comets? Enter the deeper story. Over unimaginable spans, interstellar radiation doesn't merely weather a surface, it re-engineers it. JWST's NIR spec data and modeling efforts argue for a thick, radiation-processed rind on the order of 15-20 meters deep, where cosmic rays rearranged chemical bonds, converted CO to CO2, and altered the mechanical properties of the outer shell. Think of it as armor, forged by the galaxy itself. The hope many of us quietly nursed, that an interstellar comet would deliver pristine samples of another star's nursery, meets a caveat. What we're seeing from afar may be the product of the journey, not the birthplace. The rind may not tell us how 3I Atlas began, it tells us how it survived. That's the conservatively stated half of the picture. The new half is the unsettling question that follows. If a hard, irradiated shell capped more volatile layers, the sudden perihelion snapped surge implies a threshold phenomenon. Thresholds can be natural, reach the right temperature, pressure regime, crack the shell, ignite rapid outgassing, and off you go. But thresholds are also what engineers love. We build instruments that sleep until a flux crosses a line. We design systems that arm only at a specific stimulus. No one should leap from threshold to artifact. Still, the diagnostic challenge is the same. Can we distinguish a physical threshold in a messy natural body from a deliberately tuned one? Most of the time, yes. Nature leaves fingerprints in the stochastic details. That is precisely why the next weeks of data, as the comet recedes, matter. There's another wrinkle. The coma seemed gas-heavy and dust-poor. In the solar menagerie, dust is the press agent, bright, dramatic, sculpted by light pressure and plasma flows. If dust is muted, either the solid's inventory is intrinsically low, the grains are unusually cohesive and reluctant to loft, or they were ground into sizes that scatter light differently than we expect. Each pathway implies different internal physics. Cohesion could be enhanced by irradiation sintering, A dust-poor composition could reflect formation in a carbon-rich, metal-poor corner of some long-gone disk. Ultrafine grains could clump into optically subtle aggregates. Any of these can suppress a classical tale. But whichever explanation we favor must also reconcile the abruptness of the brightening, the blueward spectral tilt, and the high water production rate. Stitching those into a single self-consistent picture is the work. Let's zoom out and place 3I Atlas in the austerely small club of interstellar visitors humanity has watched up close. First came Oumuamua, famously weird and frustratingly faint, then 2I Borisov, which looked more like a normal comet with a foreign passport. Now 3I Atlas, which has arrived to break rules in its own way. With a sample size of 3, our priors should be flimsy. The galaxy's cold-chain logistics are not obliged to make its drifters look uniform. If anything, diversity is the expectation. Yet even with that humility, 3I Atlas is forcing us to question which parts of comet behavior are universal physics and which are parochial habits learned in our heliosphere. That irradiated rind is a clue to survivability. Picture billions of years as a slow kiln. Cosmic rays and micro-impacts, compact porous ice, stitch organics into tougher polymers and anneal voids. The shell becomes denser, less dusty, and more fracture-prone, until heating drives internal pressure that propagates cracks like lightning. Once open, volatile pathways channel gas through a maze that was sealed for epochs. This view naturally produces silent boom light curves near a star, long quietude, then a sharply rising phase when a percolation threshold is crossed. It also naturally produces directional asymmetries. Vents are not a uniform mist, they're biased by fractured geometry. If subsequent astrometry shows a non-gravitational acceleration aligned with specific venting directions, we'll chalk more of this to physics we already grudgingly understand. On the other hand, if thrust vectors persist without accompanying jet diagnostics, or if activity repeats in quasi-periodic pulses decoupled from insulation, we'll have to widen the hypothesis space. There are intermediate possibilities that still keep us in natural territory, phase transitions in mixed ices that release latent heat in bursts, clathrate, uncaging that freeze trapped gases on heating cycles, electrostatic lofting in the innermost heliospheric plasma environment, even magneto-hydrodynamic coupling between ionized coma species and the solar wind that modulates mass loss on timescales governed by plasma instabilities rather than sunlight. Each carries predictions we can check: radioline variability, UV fluorescence ratios, coma polarization, in situ solar wind conditions at the time of surges. The absence, so far, of a canonical dust tail is more than an aesthetic quirk. It reshapes how we interpret brightness. Gas emission lines and continuum scattering by tiny grains can masquerade as a brighter comet without a proportionate dust mass. That matters because dust carries much of the momentum budget in sublimation-driven jets. Less dust means less thrust per kilogram of gas, which influences the size of non-gravitational accelerations we expect. If later we detect a measurable trajectory push, but continue to see gas-heavy dust-light spectra, we'll face a paradox that demands either unseen dust modes or alternate physics. Again, testable, not mystical. There's a related, quieter revolution tucked inside this event: how we think about planet formation. One provocative set of models proposes that interstellar interlopers can seed young disks, ready-made kilometer-scale bodies that short-circuit the meter-size barrier where collisions grind aggregates back to dust. If that capture and seed mechanism is common, then 3I Atlas is not an orphan. It's a representative of the raw inventory from which planets elsewhere may have formed. That notion doesn't require exotic explanations for today's anomalies, but it gives them weight. Understanding 3I Atlas is not only about a single comet gone strange, it's about calibrating a galaxy-wide delivery system for worlds. And then, of course, there's transparency. When nature overturns neat theory, the best response is to open the books. Spectra, photometry, astrometry, coronagraph stacks, polarization maps, plasma environment reconstructions. Dump them all into the commons and let many minds stress test interpretations. This is not a referendum on any single instrument team. It's a recognition that rare events demand maximal eyes. The stakes are straightforward. 3I Atlas will fade. We do not get replays. If the outer rind truly is a radiation product and solar heating has scraped a window into deeper layers, the interval right now, weeks to a few months, may be the only chance to compare before and after chemistry. If the object keeps surprising us post-perihelion, we'll need the raw material to cross-correlate signatures across facilities and wavelengths. What we already know is enough to justify the intensity. The light got bluer, the water dump spiked, the tail underperformed. The images show an oddly elongated glow hugging the sun's edge. The candidate explanations are many, but their consequences are concrete. Follow-up visible near-IR spectroscopy can map the CO-CO2 H2O balance as the solar heating falls. UV lines, OCN, can track volatile sourcing and lifetimes. Narrowband imaging and polarimetry can sniff out otherwise invisible dust. Careful orbit fitting can isolate non-gravitational terms and test whether any thrust aligns with observed venting. Even the solar wind's temperament during the peak could matter. CME-driven changes in local fields can reshape comi in ways that mimic internal changes if you're not watching the plasma. So, no, this is not just another comet. It is an object that spent perhaps billions of years in the black between stars, rolling the dice against collisions, radiation, and tidal shredding, and then, on its short pass near our sun, chose to write its story in sharp, jagged pen strokes rather than smooth curves. That alone makes it precious. The conservative scientist and the adventurous one agree on at least this. When reality hands you a puzzle with missing pieces and a clock ticking down, you gather every shard you can and compare them ruthlessly. If 3I Atlas quiets and fades along a revised, still natural model, we'll have learned how interstellar weathering sculpts cometary behavior. If it refuses to be domesticated by those models, we'll have learned something even more valuable: which questions to ask next. For now, we hold two truths at once. The safest explanation is that 3I Atlas is a natural body with alien childhood memories and a hardened adult shell, and the correct posture is radical empiricism: measure, share, falsify, repeat. Somewhere inside its bright, blue-tinted breath is the answer to why it erupted when it did, and why it wears so little dust. Somewhere beneath that rind may still lie the chemistry of a different star's nursery, waiting for the galaxy's kiln to crack just a little wider. At perihelion, the numbers looked almost ordinary on paper, visual magnitude flirting with 9, until you remembered where the comet sat in our sky, buried in day glare, welded to the sun's limb from Earth's point of view. For most observers on the ground, it was observationally forbidden. You don't chase a ninth magnitude object living inside the corona with backyard glass. So we leaned hard on space-based coronagraphs and ultraviolet eyes to carry the narrative. Those instruments painted a consistent picture, a stretched, low-dust glow and a hydroxyl signature flagging vigorous water release. The piece that refused to fit was not brightness per se, but morphology, the missing dust tail where intuition swears one should stand. Dust isn't just pretty, dust is dynamical leverage. Without it, a comet's coma becomes a chemistry problem more than a scattering problem, and the usual mental shortcuts you bring from Halley or 67P stop working. Rewinding a few months clarifies the stakes. JWST's August spectra had already implied a CO2-rich regime and a surface that looked processed rather than primordial. Translate that jargon. Cosmic rays don't merely rearrange molecules, they alter mechanical behavior. You can get a tougher, more cohesive crust that resists venting until stresses accumulate. In that setting, a dramatic break at perihelion feels less like mischief and more like brittle failure. And brittle failure begets channels, localized vents that throw gas with minimal entrained dust if the fracture margins are glassy or if solids are cemented by irradiation. The spectra's blue tilt adds another facet. Gas-dominated light not only brightens differently, it evolves differently with geometry and time. That's why post-perihelion monitoring isn't optional. It's the only way to ask whether we saw a one-off shell crack or a transition to a new steady state. The next act unfolds where Earth-based instruments can finally play again. As solar elongation widens through November and December, small and mid-sized telescopes can pick up the baton with narrowband filters tuned for CN, C2, OH, and OI. Those lines let us partition the coma's budget, which volatiles are sourcing the show, and how their ratios change as insolation drops. Photometry alone can lie. Compositional light curves can't lie as easily. Pair those with polarization imaging and you can detect wisps of dust other techniques miss, ultrafine grains that polarize light differently than textbook power laws predict. If polarization stays low while gas lines roar, the dust-shy diagnosis hardens. If polarization rises weeks after perihelion while gas output falls, that hints the shell is shedding solids belatedly, perhaps as fracture networks propagate and liberate trapped fines. There's also the quiet telemetry buried in the orbit fit. Non-gravitational accelerations are the coma's confession letter. They integrate overall the messy microphysics into a single vector, which way the object is actually being pushed. If the thrust direction tracks solar geometry and the magnitude scales with gas production, you can live happily within natural sublimation models. If the thrust wanders in ways decoupled from known venting or shows step-like changes at specific heliocentric distances, then you are morally obliged to ask harder questions. Even then, harder does not mean exotic. Cloth rate release, phase transitions, or pressure-driven crack propagation can all make thrust appear in jumps. The point is to design tests that discriminate, watch for periodicities, look for phase lags between solar input and activity output, and cross-match with solar wind conditions to subtract plasma-driven artifacts. Speaking of plasma, the environment near the Sun is not a neutral vacuum. It's a storm of charged particles and magnetic fields that chew on comae. The stereo and SOHO images hint at asymmetries that could be sculpted as much by the solar wind as by the nucleus. Ion tails kink, comae flatten, and faint striae shear on timescales of hours when a coronal mass ejection sweeps past. It's easy to misinterpret those real-time contortions as intrinsic variability. The remedy is coordination, time-resolved spectroscopy tied to heliospheric monitors and MHD models. If a brightness spike coincides with a solar wind compression and comes with line-shape changes characteristic of ion pickup, it belongs to space weather, not the nucleus's secrets. All of that lives on the natural side of the ledger. The other half, the fresh content the moment demands, is a concrete checklist for falsifying the romantic interpretive leaps that crop up whenever an interstellar object misbehaves. First, impose discipline on the threshold narrative. If the perihelion spike was a stress fracture event, we should see relaxation. Vents stabilize, production decays roughly as R2 or R3, and the coma chemistry follows expected cooling trends. If, instead, activity toggles at discrete heliocentric distances on the outbound leg, say a second surge at a well-defined insolation, then you have a repeatable threshold worth interrogating. Second, do not neglect radio. Rotational lines of CO, HCN, and CH3OH can diagnose deeper sources and reveal whether volatiles are percolating through tortuous paths or erupting from fresh apertures. Third, use high-cadence photometry to search for spin state changes. Outgassing torques can modify rotation. A measurable spin-up or spin-down contemporaneous with a surge would connect activity to dynamics in a way speculation cannot. There's a broader cosmic context that deserves renewed attention, the planet seed hypothesis. If young disks capture a steady drizzle of interstellar planetesimals, then 3I Atlas-like bodies are the galaxy's courier service, toughened by radiation, carrying whatever mix of ices and organics their birthplaces provided. A hardened rind becomes a feature, not a bug. It keeps cargo intact until a warm star peels it back. In that framework, our observations aren't just about one comet's antics. They're calibration points for a galaxy-scale logistics model. Which volatiles survive giga-year transits? How often do shells crack near a star, and how much material gets re-injected into disks? Those are questions planet formation theorists can plug directly into simulations. Trajectory and age estimates add a hush to the room. A speed on the order of 130,000 mph relative to the Sun says unbound just visiting. Kinematic backtracing lands somewhere in the wide fog between certainty and conjecture, an origin in a different arm of the galaxy, a different metallicity environment, maybe a different cosmic epoch depending on the true age. The high end. Estimates 7 to 12 billion years border on audacious. Take them as order of magnitude flags, not scripture. Still, imagine what a body would need to survive that long: cohesion without gravity, armor without design. The irradiated crust offers an answer nature can plausibly supply. It is not a conspiracy to imagine that armor. It is what MeV particles do to fragile lattices when they have eons to try. Transparency remains the hinge. Calls to open the raw coronagraph stacks, the unbinned spectra, the calibration frames, and the full ephemeris fits are not provocations. They're how rare events are supposed to be handled. The community learned hard lessons from Oumuamua. Data scarcity breeds unfalsifiable stories. Borisov benefited from speedier sharing and looked reassuringly cometary. 3I Atlas sits awkwardly in between, more accessible than the first, weirder than the second. The way to keep discourse anchored is to multiply independent reductions. If multiple teams using different pipelines recover the same color trends, line ratios, and thrust vectors, interpretation will converge even if the story remains strange. There is no shame in strangeness. There is only a choice in posture. We can corral 3I Atlas into premature normalcy and miss what it teaches, or we can keep hypotheses elastic and rules of evidence rigid. Elastic hypotheses mean you are willing to entertain Clath rates, percolation thresholds, dust suppression by sintering, plasma sculpting, whatever the data justify. Rigid evidence means you do not accept anecdotes, you insist on reproducibility, and you prefer predictions that can be wrong. For example, predict that CN to OH will fall as R increases if CO2 was the temporary insulator and water now dominates. Predict that a delayed dust component will raise polarization a few weeks out if fractures widen. Predict that the non-gravitational parameter A1 should shrink with the same E-folding as the OH production rate if thrust is sublimation-driven. Then test those, publicly, ruthlessly. All the while the practical cadence continues. Amateur networks can contribute flats, not just romance, coordinated time slots, standardized filters, and shared reduction recipes that make a faint interstellar coma speak coherently across longitudes. Mid-class observatories can chase high-resolution line profiles to watch gas temperatures cool and outflow velocities change. The Solar Watch fleet can flag wind regimes so we can subtract heliophysical noise from nucleus truths. If Mars rovers or orbiters snag differential vantage photometry, great, parallax, and phase angle diversity sharpen coma tomography. What happens if the comet simply fades and the weirdness settles into a revised but natural model? Then we win the boring way. We acquire a blueprint for how a giga-year-old shell shatters and how a dust-like coma cheats our expectations. What if it refuses to fade politely, and the outbound leg draws another step? Function where radiative forcing doesn't justify it? Then we also win, because we will have found a crisp place where existing models fail and where new physics, or newly appreciated old physics, must be written. Either way, the correct response is the same. Measure more, share more, and let the evidence, not our priors, decide what kind of story 3I Atlas is telling. By mid-November, the comet had moved far enough from the sun's glare to be glimpsed again. What had been a blinding mystery near the corona became a faint thread traced across pre-dawn skies, subtle, evasive, but now observable through terrestrial optics. Teams from Chile, Hawaii, and La Palma caught the first reliable post-perihelion spectra, and the early verdict was both expected and baffling. The light curve dipped, yes, but not by the standard R2 fade a textbook comet obeys. Instead, it plateaued, as if the outgassing refused to die when the solar furnace receded. Something inside 3I Atlas was still bleeding volatile material long after the skin should have cooled. That sustained activity kept astronomers awake, not because it was flamboyant, but because it was stubborn. The plateau brought the models back under interrogation. If the perihelion outburst had fractured the crust, one would predict a brief flare, followed by an exponential decay, as venting pressure equalized. But gas production held steady, sometimes even climbing in nightly photometry. One explanation was that fresh cracks continued to propagate beneath the irradiated rind, a domino chain of failures exposing deeper ice. Another, more nuanced view proposed internal heat conduction. Once the crust cracked, latent heat trapped beneath could migrate inward, triggering secondary sublimation fronts days or weeks later. A comet that behaves like a heat wave transmission line rather than a one-shot vent could easily show the long tail in activity now unfolding. More curiously, radar pings from the Goldstone dish attempted to map the nucleus's shape, though echoes were faint and noisy. The tentative silhouette emerging from deconvolution wasn't spherical, but elongated, maybe 2 or 3 times longer than wide, echoing Oumuamua's cigar-like proportions, though not as extreme. That geometry alone doesn't imply kinship, but it feeds the narrative of survival. An elongated body rotates differently. It experiences torque variations that can concentrate stress at narrow wastes. Those sites are natural breakpoints. If the perihelion flare marked such a fracture, the resulting new surfaces could have liberated ices from pristine interiors. Every spin, every thermal pulse, could then peel another layer, explaining the sustained emissions. Spectroscopic fingerprints sharpened as instruments gathered cleaner data. The C2 and NH2 bands persisted, but additional signatures emerged, faint CO overtone lines, traces of CN, and a weak continuum bump, suggesting minute dust finally leaking into space. That dust, when analyzed through polarization, showed anomalously high alignment, as if grains were elongated or magnetically oriented. Solar magnetic fields can do that, but the efficiency observed hinted at something else, perhaps charged grains sculpted by electrostatic forces within the coma itself. Plasma interactions, once again, became a central suspect. The comet's magnetic environment might be organizing matter in ways rarely seen. Amid these measurements, theorists revisited the radiation armor idea. Laboratory analogs simulating MEV bombardment of mixed ices confirmed what JWST had implied. After sufficient exposure, outer layers transform into complex polymers, tar-like, brittle, and darker than fresh ice. When heated, these layers crack not continuously, but in bursts, venting in discrete packets. Each event alters local albedo, redistributing solar absorption, which in turn shifts stress patterns. It's an elegant, self-propelling cycle. The realization that such cycles could persist over weeks or months aligned disturbingly well with the plateaued activity. Nature, it seems, had built its own feedback loop, no engineering required. Yet whispers of alternative interpretations persisted in corridors and conference threads. The precision of the perihelion timing nagged at some. The symmetry of the light curve before and after the event felt too neat for chaotic fracture propagation. Data analysts plotted production rates against heliocentric distance and found an almost mathematical inflection at 0.37 AU, sharp, repeatable in both inbound and outbound legs. Was that coincidence or an intrinsic material threshold? Could chemical transitions, say crystallization of amorphous ice to crystalline, occur at that exact flux level? Possibly. Could mechanical resonance in a spinning, elongated body cause rupture only when rotational period coupled to thermal gradient? Also plausible. The point: the universe is generous with ways to mimic precision without intent. Still, a handful of voices reminded the community of humility. Harvard's Avi Loeb again made headlines by urging NASA and ESA to release all unfiltered telemetry, from raw photometric counts to attitude control data of observing satellites. Transparency is the antidote to speculation, he wrote in an open letter, and speculation is what secrecy breeds. Loeb wasn't insisting 3I Atlas was artificial. He was insisting that we not close the question before evidence had a chance to breathe. His plea resonated. Within days, the Naval Research Laboratory uploaded supplementary data from its coronagraph sequences, allowing independent teams to re-reduce the light curves. The crowd-sourced analyses confirmed the main findings. No dust-tail pre-perihelion, a gas-dominated coma, and an extended emission zone much longer than standard sublimation physics predicted. Meanwhile, computer simulations from the Royal Belgian Institute's group refined the cosmic ray exposure model. Using Monte Carlo diffusion algorithms, they estimated the crust's energy deposition history, mapping radiation dose against depth. The results suggested that beyond 60 feet, material could still be relatively unprocessed, a tantalizing zone of preserved chemistry. If any mechanism could peel away the outer shell, telescopes might briefly glimpse truly ancient matter, predating our sun. Such glimpses wouldn't just satisfy curiosity, they would recalibrate models of early stellar chemistry. Imagine knowing what volatile ratios existed in a system that formed 1 billion years before Earth. That is the prize 3I Atlas dangles before us. As the comet continued outbound, amateur networks began detecting subtle flickers, quasi-periodic brightness modulations spaced about 9 hours apart. Whether those reflected rotation or pulsating jets was unclear, but their regularity implied an organized structure. If rotation, it meant the nucleus was spinning faster than expected for its size, risking centrifugal breakup unless the material was unusually cohesive. Again, the irradiated shell offered a convenient explanation. A hardened crust could survive spin rates that would disintegrate fluffier comets. The same property that confused observers near the sun might now be preserving the object as it fled into darkness. In December, a cross-disciplinary workshop convened virtually under the title Interstellar Visitors and the Limits of Comet Physics. Papers poured in, some cautious, some daring. Plasma physicists spoke about induced currents, planetary scientists about sintered ice mechanics, and astrobiologists about organics shielded by deep crusts. A unifying sentiment emerged. Whatever 3I Atlas is, it demands we treat comets as active laboratories, not frozen relics. Radiation, pressure, and time can transmute simplicity into complexity, and that complexity occasionally impersonates the inexplicable. That realization is progress. So the story's midpoint looks less like revelation and more like refinement. The wild theories, alien probes, engineered triggers, are background noise compared to the deeper lesson. Interstellar space is not emptiness, but process. It sculpts, it modifies, it teaches resilience. 3I Atlas, with its cracked shell and stubborn glow, may be the living syllabus. And as its signal fades among the winter constellations, telescopes keep chasing it, still asking the same question whispered since October. Why does this traveler, ancient and indifferent, refuse to behave like the physics we thought we knew? By late December, the interstellar traveler had crossed the 1 AU mark outward, its brightness dimming but not vanishing. Nightly spectra continued to arrive, trickling in from observatories in Chile, Tenerife, and Mauna Kea. Each data set told the same story in different dialects. 3I Atlas was fading more slowly than physics permitted. The canonical models, which predicted a swift exponential decline after the sun's heat receded, had to be rewritten yet again. Something within the comet seemed to defy thermal inertia, as though its interior retained warmth longer than porous ice should. That contradiction became the new focus. If 3I Atlas carried a secret, it wasn't in its brightness anymore, it was in its persistence. One explanation began with the shape. Radar and photometric modeling hinted that the nucleus wasn't just elongated, it might also be hollowed, a lattice rather than a solid block. A porous internal network can trap solar energy deep inside, releasing it slowly as the object cools. Thermal lag, in this scenario, is not a mystery but a feature of architecture. As heat seeps through cavities filled with volatile ices, each pocket becomes a miniature geyser factory, activating at different times. That could explain the near-constant outflow, the faint periodic flickers, and even the symmetrical rise and fall of its light curve around perihelion. It was like watching a dying ember that refused to go dark. Another camp proposed a subtler mechanism, phase transitions in the ice itself. Amorphous water ice, when exposed to warming, crystallizes and releases latent heat, along with trapped gases. If 3I Atlas was built mostly from amorphous ice, a likely scenario for an ancient interstellar body, the crystallization front could crawl slowly inward, continuing long after sunlight waned. That process would mimic an internal power source without violating physics. The glow would be sustained, the jets would pulse, and the object would appear almost alive in its response. It was chemistry masquerading as biology, and it fit the observations neatly enough to calm the room, at least for a while. Yet, as always with this comet, neatness was fleeting. The latest photometric data from the Hubble Space Telescope revealed something disquieting. While overall brightness decreased, certain spectral lines, particularly CN and OH, grew erratically stronger. The ratio of CN to OH rose when it should have fallen. That ratio normally tracks temperature, dropping as a comet cools. But 3I Atlas inverted the rule. Either new volatile reservoirs were opening unexpectedly, or there were compositional layers releasing different gases at different times. In other words, the comet was peeling itself like an onion, each skin with its own chemical accent. The implications were profound. If the outer crust was indeed transformed by cosmic rays, then beneath it lay strata that recorded the environment of the comet's birth star. Imagine a time capsule sealed billions of years ago in a different stellar nursery, now venting its ancient breath into our detectors. That possibility electrified astrochemists. If we could decode the isotopic ratios, DH, 13C, 12C, 15N, 14N, we might glimpse the fingerprint of a system older than our Sun, perhaps even from an epoch when the Milky Way's spiral arms were still forming. To them, 3I Atlas wasn't just breaking comet laws. It was rewriting the origin story of cosmic material exchange. Meanwhile, the theoretical frontier pushed further. A group at the Max Planck Institute built a simulation treating the comet's interior as a hybrid. Pockets of crystalline ice embedded in a matrix of irradiated organics. When heated, the mismatch in thermal expansion caused mechanical resonance, tiny vibrations that propagated through the body, periodically cracking the crust from within. This thermal heartbeat could produce quasi-regular pulses in outgassing, precisely what the observers had been noting. It was an elegant unification of data and theory. The comet was singing to us through physics alone, its rhythm dictated by ancient damage and present heat. Still, not everyone was satisfied. Some voices insisted that the thermal heartbeat model failed to explain one peculiarity. The comet's continued high-speed non-gravitational acceleration detected in trajectory fits. The acceleration vector wasn't random. It lined up almost perfectly with the object's long axis. Natural venting tends to wobble that vector over time, but 3I Atlas's push remained stable. That kind of consistency hinted at symmetry, a distribution of jets too uniform to be accidental. Engineers in the audience smiled quietly. Uniformity is what you design when you want stability. Once again, the uncomfortable question resurfaced. Could such precision arise by chance? NASA's Jet Propulsion Laboratory weighed in cautiously. In a technical memo released to collaborating observatories, they modeled the effect of symmetric venting across a bilobed nucleus, similar to Comet 67P Churyumov-Gerasimenko. If two large vents on opposite ends of an elongated body outgassed in tandem, they could yield an overall acceleration vector along the major axis without rotation. It was, at last, a natural explanation that fit the data. But even that scenario raised deeper puzzles. How did such perfect bilateral vents form in an interstellar wanderer never sculpted by solar tides or planetary passes? Was the symmetry coincidence, or was it inherited from its formation environment, a frozen echo of dynamics in a foreign disk? The broader community took notice. Interstellar object research, once niche, now occupied prime sessions at conferences. For the first time, planetary scientists, plasma physicists, and astrobiologists shared the same language, bound by this one comet that refused to behave. 3I Atlas became a bridge subject, a reminder that cosmic boundaries between stars, between disciplines, are porous. Journal editors noted an uptick in cross-field submissions, papers blending chemistry and dynamics, radiation physics, and evolutionary modeling. In a quiet way, the comet was forcing human science to imitate its own hybrid nature, layered, complex, unwilling to stay in one category. Public interest reignited too. Media outlets dubbed it the Rebel Comet, headlines echoing the sentiment that the universe was teasing us again with a mystery just out of reach. But behind the drama, real questions loomed. If interstellar objects like 3I Atlas carry the chemical heritage of extinct star systems, how many wanderers have already passed unseen? How much of our own solar system's raw material came from similar migrants billions of years ago? Are we, in some subtle sense, children of many suns? These were the questions scientists began to ask, not in speculation, but in calculation, writing new models of galactic matter exchange. Even as the comet drifted outward, now faint and pale against the deepening winter sky, the intrigue deepened. Observatories reported occasional micro-outbursts, minute spikes in brightness, each lasting less than an hour. Too short for conventional sublimation fronts, too frequent to be random, they looked almost rhythmic. The term pulsed venting entered the literature. Each pulse carried its own spectral fingerprint. Slightly different CN to OH ratios, slightly altered dust scattering profiles. It was as if different pockets within the nucleus were taking turns exhaling. The data made for mesmerizing graphs, saw-tooth patterns where a simple curve should be. By the end of the year, the world's major telescopes had hundreds of hours of data, and the real synthesis began. Teams combined thermal modeling, radiation chemistry, and plasma dynamics into a mosaic of possibilities. None fit perfectly, but together they painted a larger truth. 3I Atlas was not violating physics, it was teaching physics. It was reminding us that our models, built on comets born in one modest solar nursery, cannot yet account for the full diversity the galaxy manufactures. Every rule it broke was really a boundary of our own experience. And still, behind every rational explanation, the whisper persisted, a low hum of curiosity too ancient to silence. Maybe that hum was why telescopes kept tracking long after the object dimmed past visibility. Because somewhere in its erratic light, scientists could feel a pulse, faint but undeniable. A reminder that even after billions of years drifting through darkness, the universe still knows how to surprise us. By early January 2026, 3I Atlas was a whisper in the telescopes, a faint bluish point crawling away from the sun, fading toward the edge of detectability. Yet its story refused to fade with it. The comet had become less an object of observation and more a case study, an evolving hypothesis machine that forced every assumption about interstellar debris back onto the drawing board. Even now, the comet's residual outgassing continued to surprise. Swift's ultraviolet telescope recorded that its OH emission fluctuated with the solar wind's changing polarity, as though the coma itself responded to magnetic pressure instead of mere sunlight. This was uncharted territory. Standard models treat a comet's coma as a passive veil, reacting thermally, not magnetically. But here, plasma density and gas emission seemed to rise and fall in lockstep. That correlation suggested an active coupling between the solar wind and the ionized gases surrounding 3I Atlas, a dynamic more like a magnetosphere than a coma. If confirmed, this behavior would mark the first time an interstellar body displayed magnetohydrodynamic feedback on such a scale. Theorists from ESA's Solar Orbiter team ran simulations showing that a thin ionized sheath around an irregular conductive nucleus could trap charged particles and oscillate under solar wind impact. Those oscillations might drive the pulsed venting previously seen, plasma acting as both sculptor and metronome. It was an elegant bridge between plasma physics and comet dynamics, and it explained why the emission spikes persisted long after solar heating waned. Meanwhile, the James Webb Space Telescope kept its infrared eyes on the fading glow, scanning for any residual thermal anomaly. Instead of cooling predictably, the nucleus retained heat longer than the models predicted, reinforcing earlier suspicions of a dense, insulating crust. Data indicated that the temperature gradient between core and surface remained nearly constant for weeks, implying internal heat reservoirs or low-conductivity materials. It seemed the interstellar traveler wasn't just ancient. It was a master of thermal patience. This odd thermal behavior reignited an older question. How had it survived its billion-year journey intact? Most comets born within our own solar system fall apart after a few perihelion passes. An interstellar object exposed to cosmic radiation, stellar encounters, and micrometeoroid impacts for billions of years should be rubble. Yet here it was, cohesive, massive, and durable enough to endure a close brush with the sun. The crust hypothesis gained new weight. Radiation chemistry had forged something like a carbon-ceramic armor, resistant to both heat and disintegration. If that armor formed naturally in interstellar space, then the galaxy could be littered with objects built by physics into endurance machines, comets that never die, only evolve. But nature's endurance raises existential echoes. A few researchers dared to entertain the unsettling thought that perhaps this durability isn't random. If you were designing a probe to drift for billions of years, one astrophysicist half joked at a symposium, you'd want it to look exactly like this. No one in the room laughed because the joke was too close to the frontier where speculation becomes hypothesis. A body shielded by a radiation-forged shell with thermal regulation, threshold-triggered outbursts, and near-symmetric acceleration vectors, it ticked boxes familiar to engineers, not just astronomers. To ground the discussion, NASA's Jet Propulsion Laboratory published a technical rebuttal. Their paper meticulously demonstrated that the comet's mass, roughly 33 billion tons, could account for the stability and endurance without invoking exotic materials. The mechanical strength required for its survival fell within the limits of naturally irradiated carbonaceous ice. They emphasized that the coincidence between symmetry and persistence was not evidence of intent. Yet even JPL's closing remarks admitted an intriguing truth. We lack an adequate sample size to generalize interstellar object survivability. In essence, they couldn't explain it fully, but they could model it enough to sleep at night. Parallel to these debates, new measurements emerged from Mars. Both the Curiosity and Perseverance rovers had captured high-contrast images of the comet from their different longitudes, tiny pinpricks, but enough for triangulation. These Martian observations offered a rare geometric advantage, parallax data from a different solar vantage. The analysis refined 3I Atlas's trajectory to an even more precise escape vector, one almost perfectly planar with the ecliptic, suggesting that the comet's inbound path had been influenced by something massive long before it entered our neighborhood. Whether that was a distant stellar encounter or a relic gravitational assist from a binary system remains unknown. What was clear is that this was no random wanderer. Its path was too clean, its arrival too geometrically elegant. As the data accumulated, a new paradigm quietly took root among planetary scientists. Instead of viewing interstellar comets as oddities, they began to see them as a population, a vast, invisible archipelago of travelers connecting stellar systems. If even a fraction of these bodies shared 3I Atlas's resilience, then the Milky Way might be perpetually exchanging material between its stars, a slow, silent commerce of molecules and minerals. The galaxy, in that view, is not a set of isolated islands, but an ecosystem with cosmic currents. 3I Atlas wasn't breaking laws, it was revealing them. The intellectual momentum reached the public. Media outlets that once framed the comet as a curiosity began running features on the galactic conveyor belt, the idea that objects like Atlas transport ingredients for life across interstellar distances. Scientists, usually wary of hype, allowed themselves a rare indulgence, wonder. Because if the radiation shell preserved organics as well as ice, then 3I Atlas might be a vector, a delivery system for chemistry older than Earth itself. That possibility made even the most skeptical researchers pause. In Cambridge, Loeb and his small team published an open-access dataset compiled from public observatories and crowd-sourced imagery, creating a live archive anyone could study. They called it the 3I Commons, a gesture toward the collaborative spirit that had defined the investigation. Within days, citizen scientists began finding faint correlations, periodicities in brightness curves, subtle alignments in gas jets that professional analyses had missed. A pattern emerged, faint but persistent. Every 27 hours, the comet's light shifted slightly in color, an oscillation invisible in single night runs but clear in stacked time series data. The source of that periodic color shift remains debated. Some attribute it to rotational modulation, others to plasma cycling. Either way, it suggested that even as it receded, 3I Atlas continued to communicate through its rhythm. At this stage, scientists agreed on one thing: whatever the comet's origin, its behavior was rewriting the limits of known cometary physics. They no longer spoke of violations of laws, but expansions of them. It had not so much broken 9 laws of comet physics as reminded us that our laws were regional, not universal. In the vast dark between stars, other rules can apply, other chemistries can reign. By the time January's last week arrived, 3I Atlas was slipping past the reach of all but the most sensitive instruments. The light grew fainter each night, its signature stretched thin by distance. Yet, as it receded, it left behind a paradoxical brightness in human minds. We had not solved the mystery, only deepened it. But in that deepening, something vital had happened. Science had remembered its oldest posture, the posture of wonder. And so the data flowed one last time from the cold, silent visitor, a thin stream of photons carrying stories from a forgotten corner of the galaxy. Somewhere beneath that hardened crust, in the black quiet of interstellar time, a nucleus of ancient ice still turned slowly, unchanged by the questions it had provoked. It came, it shone, it broke our models, and then it left, proof that the universe still keeps secrets worth chasing. By February 2026, 3I Atlas had dwindled to a mathematical ghost. A few dozen photons on stacked exposures, a whisper traced through the noise by software more sensitive than sight. But though the comet itself was gone from the sky, its wake in human thought was still widening. Data archives swelled, models multiplied, and the event that had begun as a fleeting anomaly now sat at the center of a quiet revolution in planetary science. The final composite images from JWST and Hubble painted a strangely poetic ending. The comet's coma had flattened into an elongated plume that no longer glowed, merely reflected. It shimmered faintly in scattered sunlight, a last gleam before anonymity. But its spectrum told a final secret: complex hydrocarbons, not just simple ices. The mid-infrared features at 3.4 and 6.2 microns pointed unmistakably to long-chain organics, polycyclic aromatic hydrocarbons, or PAHs, the building blocks of prebiotic chemistry. That discovery reframed the entire narrative. 3I Atlas wasn't just ice and rock from another system. It was chemistry that might have belonged to life's distant cousins. The public headlines wrote themselves: alien chemistry in the interstellar comet. But the scientists were more careful. Alien here meant non-solar, not biological. Still, the implications rippled across disciplines. If interstellar comets routinely carry PAHs, then the galaxy may be seeded with these molecules by natural transport, drifting laboratories spreading the precursors of life from star to star. In that view, panspermia was no longer a fringe speculation, it was a chemical inevitability. At the Lunar and Planetary Science Conference in Houston that spring, the 3I Atlas sessions were standing room only. A slide from the Tokyo Institute team drew audible murmurs, a model showing how an interstellar object with a hardened, radiation-forged shell could retain organics for billions of years without decay. In the simulation, the PAHs beneath the crust acted as self-shielding pigments, turning the body's surface progressively darker and more thermally stable. The comet, in essence, had armored its own memory. That realization birthed a new term in the literature, exocryogenic archivists. These were bodies like 3I Atlas, relics from extinct planetary systems, still carrying chemical records of places that no longer exist. The notion that a lump of ice could be an archivist for lost worlds changed the tone of the conversation. Scientists stopped speaking of a comet and began speaking of a messenger. In March, a final coordinated campaign between Earth and space telescopes closed the observation window. The outbound trajectory confirmed the last paradox. Even at more than 1.8 AU, the comet still displayed weak but measurable, non-gravitational acceleration. That meant some level of outgassing persisted far beyond the thermal range of active water ice. CO, CO2, or even trapped hydrogen might be the culprits, but none of those fit the faint, stubborn rhythm of emission recorded by the instruments. Whatever the driver was, it operated at an efficiency no ordinary physics had predicted. NASA's report ended with an admission rare in official documents. We are now confronting the limits of our cometary taxonomy. 3I Atlas may represent a transitional class of interstellar object, one in which radiation-induced metamorphosis has produced behaviors not seen in solar system analogs. Further study awaits the next visitor. That last line was both resignation and prophecy. For every mystery the comet left behind, it also left a blueprint, how to catch the next one, how to instrument the encounter, how to listen when the universe speaks again, through the small and the silent. Yet even as the observatories turned away, a strange cultural afterglow began to bloom. Artists, poets, and musicians seized upon the story, the ancient traveler that outlasted its star, the cosmic ember that refused to obey. Concerts titled Rind of Fire, exhibitions named The Visitor's Breath, novels imagining civilizations born from such comets. The mythos spread. 3I Atlas had crossed the boundary from data into narrative, from science into symbol. Back in the scientific world, work continued in quieter ways. Laboratories replicated the bombardment of cosmic rays on icy organic mixtures, confirming that the radiation rind could indeed generate polymer layers strong enough to survive perihelion-like heating. Plasma physicists explored how an ionized coma might couple electromagnetically with the solar wind to sustain periodic activity. Astrobiologists began mapping the stability of PAHs in those same environments, finding that interstellar radiation didn't necessarily destroy them, it evolved them, producing complexity from simplicity. The consensus that emerged was paradoxically humble. 3I Atlas was extraordinary, but not unique. The Milky Way, it now seemed, must be filled with such emissaries, a diffuse, invisible fleet of frozen seeds drifting between stars, waiting for heat or gravity to awaken them briefly before returning to darkness. Humanity had caught one only because timing, geometry, and luck aligned for a moment. By summer 2026, the final composite dataset was published: spectral cubes, photometric time series, plasma field reconstructions, and trajectory fits. Thousands of researchers downloaded the files, and the comet's faint signature lived on as digital light. The physical body was gone forever, beyond Pluto now, outward into the cold. But the data had become its second life, a durable echo in human archives. And perhaps that was fitting. For an object that had drifted unobserved for billions of years, what greater immortality could there be than to be remembered, not as a mystery to be feared, but as a messenger that deepened our wonder. Somewhere, far beyond the heliopause, 3I Atlas turned silently among the stars again. Its crust is cold, its heart asleep, but if one were to listen closely, impossibly closely, one might imagine a faint rhythmic beat, like the echo of a cosmic clock still ticking, not mechanical, not engineered, simply the slow breathing of physics across time. And in that rhythm the universe whispers its oldest lesson, "You have not yet seen all that I can be." By autumn 2026, the dust had settled, literally and metaphorically. 3I Atlas was gone beyond the heliosphere, its trajectory carrying it toward interstellar night. Yet in laboratories, data centers, and conference halls, its ghost kept speaking. Researchers began to notice how every anomaly it had shown, the bluing spectrum, the delayed thermal release, the pulse-like jets, now formed a coherent story when viewed through a single lens, radiation evolution, as a creative process. It turned out that 3I Atlas was not just a survivor of the galaxy's violence, it was a product of it. Over billions of years, cosmic rays, UV photons, and micro-impacts had transformed its outer layers into something new, not dead, but reactive. The shell that had perplexed astronomers for months was now recognized as a kind of chemical armor, a matrix of carbon-rich polymers that both protected and modulated what lay beneath. When the comet finally neared the Sun, that armor fractured along patterns written by eons of energy. Its strange behavior wasn't rebellion. It was memory, memory expressed in heat and light. The Atlas hypothesis, as it came to be known, soon extended beyond cometary science. Planetary physicists began to apply the same principles to small moons, Kuiper belt objects, even asteroids with volatile traces. Could radiation forging be the missing factor behind puzzling thermal anomalies on bodies like Chariklo or Arakoth? Could cosmic aging be as formative as planetary birth? These were not rhetorical questions anymore. 3I Atlas had given them data to work with. In December, a multinational collaboration released a model called Intercoma, a numerical simulation that treated interstellar comets as evolving organisms, chemically and structurally, rather than static relics. In the simulation, a virtual body similar to 3I Atlas acquired a dense outer crust over hundreds of millions of years, altering its reflectivity, fracture mechanics, and volatile release patterns. When dropped into a solar-like system, the model reproduced every oddity of the real object: the brightening surge, the asymmetric jets, the stubborn blue hue. What had seemed inexplicable now emerged as predictable once the timeline stretched far enough. And yet, even as explanations accumulated, the sense of wonder did not fade. Because beneath the neat equations lay something profound, the realization that interstellar comets are storytellers of time. Each carries the narrative of its origin star, its eons of wandering, and its brief conversations with new suns. Each is both artifact and experiment, a moving archive of galactic chemistry. This idea changed the tone of exploration planning. ESA and NASA jointly proposed a mission concept named LUCID, Long-Range Unbound Comet Intercept and Diagnostics, a fast-response probe designed to rendezvous with the next interstellar visitor. The craft would sit in solar orbit, on standby, equipped with high DV thrusters, ready to sprint toward any incoming body detected early enough. Its payload, mass spectrometers, radar, and dust collectors designed specifically to sample a radiation rind without destroying it. The mission brief, quietly poetic, read, to touch what the galaxy has made in silence. Funding debates were fierce, but public fascination tipped the scales. 3I Atlas had already proved that these travelers were not once-in-a-millennium flukes. They were frequent, invisible guests. Statistical modeling from the Pan-STARRS archive suggested that, at any given time, tens of interstellar objects are crossing the inner solar system, simply too faint to notice. With better sensors and a little luck, humanity would meet another soon. Culturally, the comet's legacy deepened into something mythic. A year after its passage, the rebel comet had inspired symphonies, documentaries, and even the naming of an orbital art installation. The Atlas Resonance, a slowly rotating mirror array that modulates sunlight into a faint heartbeat visible from low Earth orbit. The installation's designer explained, "It's our way of giving the sky back the rhythm it gave us." Meanwhile, new data reprocessing continued to reveal subtleties. Hidden within Hubble's ultraviolet observations, researchers found faint periodic absorption lines indicating possible traces of nitrogen-bearing organics, molecules complex enough to suggest prebiotic chemistry preserved since the object's formation. That discovery linked directly to laboratory studies showing that under cosmic radiation, such molecules can self-organize into chains capable of catalyzing further reactions. The boundary between comet and protocell grew even thinner. At the same time, a philosophical current emerged. 3I Atlas had reminded scientists and poets alike that longevity is not the opposite of fragility, but its consequence. The very brittleness of its shell, born from exposure and time, was what allowed it to break open and release new chemistry when warmed. There was something metaphorical there, that endurance and transformation are not mutually exclusive, even in the cold vacuum between stars. By early 2027, the last peer-reviewed volume of the Atlas cycle was published, Interstellar Objects as Agents of Galactic Ecology. The title sounded grand, but its premise was simple, that every drifting comet, every frozen shard ejected from some lost system, participates in a slow, continuous exchange that keeps the Milky Way chemically alive. 3I Atlas had been one such messenger, and somewhere, deep in that cold beyond, it still is. Its shell, cracked but unbroken, glides through the void, carrying within it a record of two suns, the one that made it and the one that briefly illuminated it. It will not return. Its path is infinite, but the photons it left behind remain, etched into our detectors, our code, and our imagination. The final line of the last paper on the comet, signed by hundreds of authors from 20 countries, reads, 3I Atlas departed, but it did not leave us the same. We thought we were studying a comet. What we found was the continuity of the galaxy itself. And so ends the chronicle, not with disappearance, but with inheritance. The next time a dim, foreign light enters our sky, humanity will already be listening differently, not merely to see what it is, but to ask what long-forgotten story it carries on its frozen breath. By mid-2027, the last echoes of 3I Atlas had faded from active observation, but the world it left behind looked subtly transformed. In universities, young researchers were beginning their careers under what some called the Interstellar Renaissance, a movement that saw the cosmos not as a static museum of stars, but as a living exchange network, one where every fragment drifting through space carried meaning. The laws that 3I Atlas had broken were no longer treated as violations, but as revelations of a deeper order, physics expanded by patience, chemistry rewritten by time. Across observatories, data from the comet's brief visit was being reprocessed with new algorithms. Machine learning models built to detect faint nonlinear periodicities began finding echoes in the noise, minute fluctuations in the archived spectra, too small for the human eye but consistent across instruments. Those oscillations matched none of the known cometary modes. The signature was quasi-harmonic, repeating every 1.13 days with a precision bordering on mechanical. Was it a rotation resonance or something else? The papers argued endlessly, but none could agree. Some described it as an intermittent thermal cycle, others as a relic pattern of deep core crystallization. A minority suggested it might represent a residual electrical oscillation, tiny discharges within the crust, triggered by cosmic ray hits like the slow ticking of a frozen capacitor. The idea sounded poetic and absurd, yet the math fit. The comet might still be alive in the most literal physical sense, exchanging charge with the void. NASA's Lucid mission, now formally approved, was already under construction, its frame designed from carbon composites engineered to withstand decades of dormancy. The plan was bold: launch it into a wide solar drift orbit where it would wait silently until another interstellar object was detected. The moment sensors on Earth picked up a candidate, Lucid would awaken, compute an intercept trajectory, and burn toward the intruder. Humanity would no longer be a passive observer of cosmic visitors. It would be ready to meet them halfway. 3i Atlas had made that possible, not by command but by example. Meanwhile, in quiet corners of academia, philosophers and scientists began collaborating again, something unseen since the Renaissance. The comet had reopened questions thought long closed. What defines an object as alive? Can matter, shaped only by time and radiation, exhibit behavior that mimics intention? If patterns can emerge from randomness that seem to respond to conditions, is agency an illusion or a continuum? Papers with titles like Entropy as Biography and the Memory of Ice began appearing in journals once allergic to metaphor. The comet had melted the wall between physics and meaning. Public fascination persisted too. In classrooms, children drew spiraling comets labeled messengers. In digital art galleries, AI-generated renderings of 3i Atlas, half-melted, half-transcendent, hung beside sonified data tracks. The hum of its spectra turned into music. People could listen to the sound of an interstellar visitor, a slow pulse of light transformed into rhythm. It felt like contact, not with aliens, but with the universe itself. Then came an unexpected epilogue. In late November 2027, the Pan-STARRS network detected a faint, high-velocity object entering from the outer heliosphere. Its motion was linear, its color index redder than 3i Atlas, but equally foreign. Preliminary trajectory estimates showed it was interstellar, inbound at nearly the same inclination. The catalog designation was 4i, its provisional name to follow. The coincidence was uncanny. The scientific community held its breath. Was this a sibling? A fragment from the same ancestral system? Or simply the next traveler in the endless tide? Within weeks, Lucid's mission control received its first activation command. Engineers watched as the probe's systems warmed from hibernation, aligning thrusters, recalibrating instruments, running through protocols written years earlier under the shadow of the first interstellar visitor. Humanity's response this time was immediate, deliberate, prepared. When the engines ignited, a ripple of excitement passed across the world. We were no longer waiting for the unknown to pass by. We were going to meet it. But even as this new pursuit began, the legacy of 3I Atlas remained the emotional axis. Scientists would cite it as the moment our curiosity outran our fear. Before Atlas, the unknown was a problem to solve. After Atlas, it became a relationship, a conversation between minds of flesh and the mindless patience of the cosmos. The last panel discussion dedicated solely to the comet took place in Geneva, under the title, "What Remains of the Visitor?" The closing speaker, an elderly astronomer who had tracked Atlas since its discovery, said quietly, "We expected to measure a rock. Instead, we were measured by it. It revealed the boundaries of our certainty, and that is the truest gift science can receive." That sentence outlived the conference, quoted endlessly afterward, because it captured what everyone from engineers to poets had come to feel, that 3I Atlas had not merely crossed the solar system, it had crossed us. It changed how we defined a law, how we defined a question, and even how we defined home. By 2028, as the new object approached its perihelion, a small plaque was mounted on the exterior of the Lucid spacecraft, engraved with a line derived from that speech. "To the travelers between suns, you showed us that even silence carries information." Somewhere, unimaginably far away, 3I Atlas drifts on, its radiation crust unbroken, its internal chemistry slowly changing in the endless dark. It is indifferent to our questions, and yet those questions now orbit it forever, bound not by gravity, but by awe. And if someday, millennia from now, another species looks up at a small, inexplicably bright comet and wonders about its origin, perhaps they too will whisper what we once did. It came from the space between stars, and it left us knowing the universe is stranger and more alive than we ever imagined.